Hi, this is Group 6, and we're here to introduce our product, the Smart Flower Pot. Growing plants has never been too easy for beginners. They tend to make many common mistakes, such as watering too much and lacking sunlight, which can lead to the death of plants. So why do we want to build a Smart Flower Pot? Because we want to help these beginners to take care of flowers and provide the extra light and water after sunset if needed. Our product can also help beginners to know the status of a healthy plant and when the plant really needs water or light. It can effectively prevent plants from dying due to the lacking of carelessness. Our Smart Flower Pot is an IoT-based system that can send data about the plant by a web application to users. It includes sensors, microcontrollers, and a communication antenna, which would be located in the flower pot. The picture on the right is a 3D design for the smart flower pot. And how we'll introduce the functionality of the smart flower pot.
We use DHT22 temperature sensor, soil monitor sensor, and BH1750 light intensity sensor to collect data from the flower pot and Arduino parsing the data. We also design an algorithm for auto watering and turn on the plant LED light automatically. For example, smart flower pots can calculate the amount of watering needed and water automatically based on the data from the soil monitor sensor and the current mode. On the other hand, the smart flower pot can calculate the effective hour of light during the day, and based on the mode, decide the hour of light are sufficient for the plant and do you need to turn on the plant LED lights. ESP01 is a Wi-Fi module for data communication between ESP8266 and Arduino. ESP8266 as a web service so that user can check the start of plants and change the mode of the smart flower pot through the web page. The ESP8266 is also connected to a OLED screen that shows the address of web page and the time. The picture on the bottom right corner is a list of some parameters of our device, such as temperature range, which is from negative 40 degrees to 80 degrees, with a accuracy in the range of plus minus half degree. Humidity range and accuracy line, dynamic range, water flow rate, and spray weightage, which are all shown in this picture. Here is the general system circuit connection diagram. All the parts are used and connected as this diagram.
Now I will demonstrate the whole system. The first thing I will show you is how to connect the system with the network by using a phone. When we open the Wi-Fi on our phone, we can see a Wi-Fi called SmartPort. It does not need a password. When we connect it, there will be a web page shown on the phone. After we click Configure Wi-Fi, the system will scan surround Wi-Fi and print their name on the phone. If we do not find the name we want, we can click Refresh below, and the system will scan again. In the video, I was looking for a Wi-Fi called Grace iPhone. I rescanned it and found it on the list. Then I clicked the name and entered the password. After saving the password, the system will automatically connect to the Wi-Fi unless we change the Wi-Fi password or we want to connect another one. The second part will show how to visit the system web page. First, we need to connect the same Wi-Fi as server, then we can get IP address provided on the LCD screen from the system. After entering the IP address, we can be allowed to access this and control the system. Here we can see the logo and the name designed by our team. Below that is the current light intensity of the plant, soil humidity, and the temperature. The customer can control the system through these 4 buttons. Each mode corresponds to a different kind of plant. Our team has researched and set up these modes for different plants. For example, in the video, I select the mode 3 and click the button. The system resolved the selection and ran the pre-written code. The next thing I will show is the automatic watering system. The system can automatically calculate the amount of water and the time the plant needed when the soil humidity is below the threshold, and then it will perform a quantitative watering. This is the data that we collect from 8 a.m. to 8 p.m. on a plant with mode 1. Here we can see that around 2 p.m. when the soil moisture percentage is below 50, the water control system was triggered. As the figure shows here, the curve starts to go up to 65% and the watering system stopped. In this part, I will show the automatic light filling function of the system. In the video, at 7 p.m., the system detects the effect light hours of the day is below the threshold. Then the system turns on the light to provide for missing hours of light during the day. The diagram in the figure shows the light intensity. The data collected before 7 p.m. forms up a parabola which indicates from sunrise to sunset. At 7 p.m., the automatic light system operates and produces the extra needed light. We still have 3 issues with the smart flower pot. The first one is the plant light is not good enough to give the plant its needed sunlight level, and our power supply will not allow higher power plant light. So we had to choose a low power light. In the future, we will improve our power supply system in order to use higher power plant lights. The second issue is our system is not waterproof. Even though we have not faced these issues yet, we are still really concerned about the water leaking. We need to design a waterproof case for our system. If we have enough time, this risk should be easy to eliminate. The last issue is the delay time. We currently have a latency of 20 to 40 seconds. There is a delay of 10 to 20 seconds between the server and the web silent. There's also a latency of 10 to 20 seconds between Arduino Uno and the server. In the future, we will optimize our hardware and some coding procedures to reduce the latency.
We have some idea about how to improve our device in the future design. The first possible improvement is combine our device with virtual assistant AI technology such as Alex, and we can use Alex to turn on and off the device by voice. The smart flower pot can say all information to Alex and is fully controlled by Alex. The second one is instead of using mod, where our smart pot can be smarter. We can create a small database. Then the user just need to enter the name of the plant, and the smart flower pot can provide the most suitable lighting, duration, and humidity according to the plant. The third one is adding a heating module for temperature control. With combination of the heating module and the temperature sensor, we should be able to create a perfect environment for your plants to grow. The first one is adding a GPS sensor can lead to more features in the future. It will allow the device to get exact information about the weather in the location area, time zone, and so on. The GPS sensor can be displayed on our website. The last one is using a Bluetooth module instead of a Wi-Fi module. With the GPS sensor in the device, we can combine it with Bluetooth and switch our device from online to the offline. It will be much more accurate and faster than using the Wi-Fi if you want to check the starter anywhere at home. This can also eliminate the large delay due to the Wi-Fi module.
Our smart pot is ideal for a small indoor plant growing system, but it can be utilized in a larger plant growing system. For example, if a farmer wants to grow a group of plants and doesn't want to waste lots of money on labor or using too much time on watering the plants, the farmer can use our system to grow their plant by just setting the plant they want to grow. This system helps them to grow the plant much easier, safer, and cheaper. So how will it work? There will be a group of water pumps that draw water from the water tank and deliver it to each plant in the area. We will have the grow lights on top, which can cover the entire plant in this area, and see if there is any need for extra light to grow plants. The owner can control our systems through their cell phone or other smart devices. The smart flower pot will have large impacts in the future. In economic impacts, this can be shown in two different ways: impacts on indoor planting and impacts on agriculture. For the economic impacts on indoor planting, people can grow fruit and vegetables at home and maintain the same amount of harvest as outdoor. People can grow plants easier, healthier, and quicker than before with our device. For the economic impacts on agriculture, as I mentioned at the last slide, in the future, if we upgrade our system to a larger scale on agriculture, farmers who use our system can grow much more food and make more money than others. In environmental impacts, plants produce oxygen, which is a priority thing for humans to live. Our system can make plants growing simpler and make the plant healthier than other ways. Also, green plants have lots of benefits, such as make people feel good, reduce stress, reduce the noise level, and help clean the indoor air. Our system can help others that are facing hunger. With the increasing amount of harvesting, people that are currently facing hunger can receive more food since there won't be a shortage of production. This is the end of our presentation, and thank you for watching.